In this video, we will discuss the trigonometric ratios. They will play a major role in all the math we do in this course. The first triangle is a right-angled triangle. That is, it has an angle of 90 degrees. It also has side lengths of 3, 4, and 5. The second triangle is also a right-angled triangle. It has side lengths of 6, 8, and 10. We immediately notice an interesting relationship between these triangles. Their side lengths are proportional. The side lengths of the triangle at right are all double the corresponding side lengths of the triangle at left. We can simplify the ratio of the sides to 3 to 4 to 5. Whenever two triangles have their sides in proportion like this, we say they are similar. And we can draw many more triangles that are similar to the first one. In fact, here's another. Its side lengths are smaller than the original, but the same proportion is maintained. Just looking at the triangle, we notice something interesting. They all look like the same triangle, just bigger or smaller versions, zoomed in or zoomed out. They are all proportionate. What do they have in common? The sizes of their angles. In fact, if you used a protractor to measure all their angles, you would see the smallest angle is about 37 degrees in all of them, and the larger angle is about 53 degrees in all of them. We can generalize this observation. If you have a right triangle where the ratio of the sides is 3 is to 4 is to 5, any right triangle with that ratio, it must contain a 37-degree angle and it must contain a 53-degree angle in addition to the 90-degree angle. Even more generally, if two triangles are similar, that is, if their sides are proportionate, their angles must be equal. Again, if the sides are proportionate, the angles are equal. Now, let's take that statement and turn it on its head. If you know that the angles in a triangle are 37 degrees, 53 degrees, and 90 degrees, then the sides must have the proportion 3 to 4 to 5. More generally, if the angles in two triangles are equal, the sides must be proportional. This sentence should also make sense because the presence of those angles forces the proportion of those sides. So you would know that a triangle with these angles must be a bigger or smaller version of the one that you see before you. You can't tell how long the sides will be, but you know they must be in the proportion 3 to 4 to 5. Let's formalize this. Consider the 37-degree angle. We can describe the sides on the basis of their relative location to that angle. The side opposite the angle has a length of 3. The side adjacent to the angle has a length of 4, and the hypotenuse has a length of 5. Remember that the hypotenuse is always the longest side in a right triangle, and it's always opposite the right angle. With respect to the 37-degree angle, the quotient of the opposite side to the hypotenuse is 3 divided by 5, or 0.6. In fact, we can generally say that in any right triangle with a 37-degree angle, the quotient of the side opposite the 37-degree angle and the hypotenuse is 0.6. This fraction, opposite over hypotenuse, is called the sine ratio, and the sine of 37 degrees is 0.6. Likewise, we can talk about the adjacent side divided by the hypotenuse. In this case, that is 4 divided by 5, or 0.8. This quotient is called the cosine. So we can say that the cosine of 37 degrees is 4 divided by 5, or 0.8. Finally, we could look at the ratio of the opposite side to the adjacent side. This is called the tangent. The tangent of 37 degrees is 3 divided by 4, or 0.5. Most of your calculations of the trigonometric functions will have to be done using a calculator. Here I'll show you how to use my calculator, the TI-83 Plus, to solve the trig functions. It might be slightly different on yours. Let us say that we want to find the sine of 10 degrees. To solve this on the TI-83, first make sure you're in degree mode. On this calculator, you have to click the mode button and then make sure that the setting is degrees, as it is. Press enter. Then press quit. Now, let us solve for the sine of 10 degrees. I see the sine button here, sine of 10, close parentheses, and press enter. 0.174. And that is the sine of 10 degrees. Your calculator can do the opposite process as well. That is, given a sine value, it can figure out what angle must have generated it. This technique, or this function, is known as the arc sine, which I symbolize like this. So supposing you wanted to find the arc sine of 0.5, that is, you knew that the sine value for an angle was 0.5, and you wanted to back calculate what the angle was. The way that you would do it is to do as follows. Another way of writing arc sine is like this. I find this way somewhat more confusing, but this is the way that it is listed on my calculator. So to do an arc sine, I would say second sine. That gives me sine to the power of -1, also known as arc sine. And I would type in arc sine of 0.5, close parenthesis, is, and I would get the answer, 30 degrees. Of course, we can do something similar for the cosine and for the tangent. So the cosine of 20 degrees is equal to cos 20, close parentheses, equals 0.94. And likewise, we can do the arc cosine. So for example, the arc cosine of 0.4 would be found using shift cosine 0.4, and we see that the angle of 66.422 degrees has a cosine value of 0.4, or equivalently, 0.4 is the cosine value of this angle. Finally, we can do it for tangent. Let's say the tangent of 45 degrees. Tan 45, close parentheses, equals 1. And lastly, I will show the arctangent. Now, the tangent function is unusual among the trig functions, because the tangent function is the only one that can produce values that are bigger than 1. If you ever try to do a sine value and wind up with something that's bigger than 1, you've made a mistake somewhere along the way. Likewise, if you do a cosine value, the cosine can also never be bigger than 1, but tan can.
And so it's perfectly fine to take the arctangent of, let's say, 2. So the way we would do it is we would say second tangent, that gives us arctangent, of 2 is 63.44. Now, all of these techniques we just saw being done using degrees. If we need to use radians, which is the other system or the other unit for measuring the sizes of angles, it's easy to do. We would click on mode and we would change the mode from degree to radian and press enter. Then second quit. Now, let us say that we want to find the cosine of pi over 2 radians. That's 1.57 radians. We would just say cosine 1.57 equals, and we would get this answer, 7.96 10 to the minus 4. It's a very small number. So we would write it like this. The cosine of 1.57 radians equals 7.96 times 10 to the power of negative 4. So this term over here, e negative 4, is a shorthand for writing 10 to the power of negative 4. And this is how you would use your calculator to find the values of different trig ratios.
As you probably know, trigonometry was independently developed by many ancient civilizations, the Greeks, the Indians, the Chinese, and many others. The history of trig is particularly fascinating. Each civilization developed trig for their own applications: construction, surveying, astronomy. They all had wildly different mathematical systems. For instance, the ancient Indians invented our modern decimal system, but the ancient Babylonians had a base 60 number system, and yet they both independently came to the same trig ratios. This tablet you see before you is from ancient Babylonia, which corresponds to modern-day Iraq. It was carved in about 1800 BCE. It contains a list of right triangles, and it might represent the earliest description of the trig ratios. This has been a quick explanation of the trig ratios we will use in this class. In the next video, we will discuss vectors.